Okay, so what we're going to be talking about here is an action potential. And in order to understand this, you kind of need to understand where this action potential is coming from. So let's say, for example, this is a cell, and it's not in the shape of a neuron or a myocardial cell or anything like that, but just for the example, it's a cell, okay? And whenever you see a graph, they're basically taking a sample of the inside, okay, of the inside of the cell in order to create this this graph that you probably very commonly see that is basically testing millivolts, right? So we have -70 here. Let's just say +30 here. I'm not going to be giving you all the details of all these things, but we're going to be talking about flux and gradient. Okay, so what's really important is that an action potential is a cell's ability to create pretty much an electrochemical gradient and to create an electrical current to allow for signaling or to allow, for example, in the heart, to allow the AV nodes to tell the heart muscles to contract. So it's all about an electrochemical gradient, basically. Chemical gradient. And what's really important is that that's created by a sodium, potassium pump. I mean, this is like the really important part that people forget about, and that this pumps out 3 sodiums and pumps in 2 potassiums constantly. This is constant. Now, why is that constant important? Well, that allows this inside of the cell. Well, let me ask you, if I pumped out 3 positives and I pump in 2 negatives, what's the overall net um, positivity of the outside versus the inside? Or I should say, of the inside versus the outside. Because remember, we're testing the inside on this graph. Basically, it'll make the inside negative. It makes the inside net negative, and it makes the outside net positive. And therefore, if I were to disrupt this cell, and let's just say there are sodium channels, that if the inside were to get a little bit positive, this sodium channel freaks out and allows sodium to like rush in, okay? If this gets a little bit positive on the inside, this allows this channel to freak out and allow this flux of sodium in, because there's more sodium on the outside than there's on the inside. And so basically there's some sort of disruption to the cell, some sort of disruption to allow that to happen. So in the case of a myocardial cell, let's say this is a muscle in the myocardium, the disruption that's allowing this cell to contract and make it the inside a little bit positive is an influx of calcium and sodium ions from the AV node telling it to do that. So let's just say AV node. And this has automaticity. And that's something we'll talk about in a different lecture. And then in the case that you may be watching this in the case of a neuron, so let's like sort of draw like a neuron here. And here's the dendrites, and here's the dendrites and the axon here. In the case of a neuron, the disruption or that little positive signaling is coming here from the dendrites from probably another neuron, right? Another neuron was signaling here and giving this thing a little bit of that positive signal, or in order to make its sodium channels open up and therefore send a positive signal down. So there's a disruption in the cell's electrical chemical gradient that's opening up this sodium ion, and that's really what's going to cause this graph. So I'm sure you've seen this graph. So right now the cell is negative. We have a disruption here that makes it a little bit positive. It passes a threshold, and that's this threshold pretty much equals how much this sodium channel can withstand that positiveness until it sort of freaks out and fires, right? Okay, so it passes this threshold, it gets a little bit positive, boom, we have an influx of sodium, and therefore the cell is becoming more positive. So this, I'm just for you to understand, this is an influx of sodium. Now I've drawn this sort of depicting a cell membrane, and this is going into the cell membrane. Notice how this is going into the cell membrane, right? but it's making the cell more positive because it was more negative to begin with. Sodium's flowing in, and then at some point, this this channel starts to close. It's like, okay, we really um, let a lot of sodiums in, and it has two phases really, which is not, that's detail for another time, but it has two like um, doors, and this door starts to close at this point. So the sodium channel closes, and then the potassium channel starts to open. And notice how I'm drawing this potassium channel going out of the cell, because now there was a potassium channel that's like, whoa, whoa, whoa. The inside of the cell got way too positive. We need a efflux, a bunch of potassium outside of the cell in order to bring this back to negative. We really want to bring this back to negative, right? And so the body's like, or the cell, I should say, is like, whoa, crap. We need to pump out that potassium, which brings this back. It overshoots. This is called hyperpolarization. Okay, hyperpolarization, right here. So it overshoots it on purpose. And then it goes back to normal again and equalizes out. And then this electrochemical gradient, again at negative 70, is maintained by that pump that we were talking about. It corrects it, and then this pump pumps at such a rate that it keeps it at negative 70. Okay? There are other things called refractory periods, where there's a certain amount of time here where the cell pretty much cannot pump again. So refractory period, the cell cannot undergo another action potential for a certain amount of time.